We have used the shopping trips example to discuss using z-test to carry out one sample hypothesis testing, right? Because z-test is for a larger sample, right? Sample size larger than 30. So now let's talk about t-test for smaller samples, okay? So suppose that in our previous example, we interviewed 20 people instead of 100 people. So this time, z-test or say standard normal distribution cannot be used. Okay, because 20 people is less than 30. And I found that the sample mean was 4.5 shopping trips per week with a sample standard deviation as 5.5. So the question is the mean number of shopping trips in this particular neighborhood equal to the mean for the entire urban area? So based on this question, suppose, right, we modify the previous example as follows. Now n equals 20, x bar is equal to 4.5, s is equal to 5.5. So step 1, 2, 3 about hypothesis setting is they are the same. Okay, so the null hypothesis is that mu equals mu 0, right? Alternative one, if we are doing two-sided tests, then it's mu not equal to, is not equal to mu 0, right? So step 4, we start from the step 4. Since n is smaller than 30 and sigma is unknown, we use t-test. Okay, so this is the formula we're familiar with, right? So here t-test is about x bar mu 0 standard deviation of the sample and also the size of the sample. Then again, according to the calculation, the t-test value is 1.14. So next step is old story. We need to find out what? Critical values, right? Find the critical value or values of the test statistic. Okay, so for alternative A1, let's say we do one-sided test, and mu 0 is still equal to 3.1. Then we need to use alpha and n-1 as the degree of freedom to use table A3 to find the critical value, which is 1.729. If we are doing two-sided test, which means that the alternative hypothesis is that mu is not equal to 3.1. We still need to find out the critical values here, but this time we do not use alpha, we use half alpha because we're doing a two-sided test, right? The degree of freedom is still the same. N is 20, 20 minus 1 is 19. Okay, so then we have a pair of critical values, right? 2.09 and negative 2.09. So step 6, similar to z-test or one sample hypothesis testing with large samples, we compare test value with critical value, right? Separately. So 1.14 is the test value, it doesn't change. And according to your alternative hypothesis, is it one-sided or two-sided? You compare that test value to different critical values, right? So for one-sided test, 1.14 is smaller than the critical value. So we are not going to reject the null hypothesis, right? And if we are doing two-sided test, still test value is smaller than the critical value for two-sided test, and then again we do not reject H0. Okay, and about the deny range and say reject range or do not reject range, t-test and z-test, they can use the same graph. I mean, t distribution and the z and the normal distribution, they are different from each other, but the shape of them is very similar. So you can simply draw the same figures like this and this for one-sided test and two-sided test to decide if your z value for your t value is within the do not reject range or in reject range. Okay, so that's the reason why here I only compared them mathematically. I did not add graphs here, so you can do it yourself. Okay, so now after talking about z-test and t-test, let's talk about the limitations of them. So the specific significance level must be selected, alpha, right, before the test, and often arbitrary and lack of theoretical basis. So alpha usually is equal to 0.05, 0.10, or even 0.01. These three typical values, they're commonly used, but it doesn't mean that they are perfectly suitable for your specific applications. So the final decision regarding the null and alternative hypothesis is binary, right? H0 is rejected or not rejected. So we may develop some more flexible method. Or in other words, what is the exact significance level associated with the test statistic? So previously, we decided the value of alpha first, then we calculate the test value or test statistics, Z or T. But this time, let's just use test statistic, try to find out this exact significance level, which means the value of alpha. So now we need to use something called p-value. P-value is the probability of getting a test statistic value, Z or Z-test or T-test, as extreme as or more extreme than that observed if the null hypothesis H0 is true. So be careful here. The big assumption here is that the null hypothesis is true. Then we can use P to address the probability of getting a Z-test or T-test as extreme as or more extreme than the observed value. Okay, so if null hypothesis is rejected, p-value is the probability of making a type 1 error. Okay. So the smaller the p-value, the more convincing to reject the null hypothesis. The larger the p-value, the more plausible H0 becomes, but we can never be certain that H0 is true. So p-value can still be considered as the area of as the size of the shaded area. If you're doing a two-sided test, okay, and you use negative z-test and positive z-test to find this two shaded area, the sum of the size of this two shaded area is p. So if z-test value, the absolute value of z, is very small, it means that it's very likely that we're not going to reject the null hypothesis. If that is the case, you can imagine a very high p-value because z-test is going to move to the left, negative z-test is going to move to the right, and of course, the size of the shaded area is going to increase. So the value of p will also increase. Right? So if it is the other scenario, z-test is going to be larger, which means it is going to the right. And the negative z-test, of course, it is going to move to the left. Then the value of p will decrease. Okay, and it's more likely that we're going to reject the null hypothesis. Okay, we're going to reject the null hypothesis. And what is the meaning of p? P is what? when the null hypothesis is rejected, p-value is the probability of making a type 1 error. So if z-test is moving to the right, it's more likely that your null hypothesis is going to be rejected. But p-value is going to be smaller, which means that it's not very likely to make a type 1 error, which means accepting a false null hypothesis. So there is always this balance. If z-test is pretty large, it's very likely that you're going to reject null hypothesis, but you're actually becoming more safe in terms of your conclusion of rejecting null hypothesis, right? You need to think through about this, the relationship between the value of z-test and p. The larger the z-test value, the smaller the p-value, the less likely that you're going to make a type 1 error, because it's more likely you are going to reject the null hypothesis. If you reject the null hypothesis, it's not likely that you are going to make a type 1 error. What is type 1 error? Accept something wrong, right? Okay, so that's p-value. So for specific example, right, the p-value in the shopping trips example, the z-test value is 2.2, right? According to this z-test value, the phi value is 0.0139. It is actually the size of the shaded area on one side of this graph. And if you're looking at the graph provided above table A2, you will see that this arrow actually points to P, right? Actually, you have known that the size of the shaded area is P. If it is a two-sided test like this, of course, p-value should be 2 times of the one side shaded area. So 2 multiply 0.0139, which is 0.0278. Okay, so what does this mean? It means that when your z-test value is 2.2, and this is the probability that you are going to make a type 1 error, which is very low. Okay, let's get back a little bit. If null hypothesis is rejected, p-value is the probability of making a type 1 error. It means that when z-test value is equal to 2.2 and you rejected the null hypothesis, then p-value is the probability of making a type 1 error. Okay, so this is the idea here. Please combine this graph, this equations, these specific values with this sentence to comprehend the meaning of p-value. Okay, and if H0 was true, the probability of getting a Z which equals or more extreme than 2.2 is 0.0278. This is actually a specific translation of this sentence. The probability of getting a test statistic value as extreme as or more extreme than that observed if the null hypothesis is true. Okay, if the hypothesis H0 is not true or is rejected, then p-value is the probability of making a type 1 error. Okay, so here, that's the meaning of 0.0278. Okay, since 0.0278 is smaller than alpha, alpha is the value we set for this example, right? We consider it not likely to happen if null hypothesis was true. Thus, it is rejected. So now here, we're not using alpha. We calculated z-test first and use that value to find the p-value for this two-sided test. That specific p-value is 0.0278. Now we compare this p-value with alpha value. Okay. Because p-value is smaller than alpha value, it is this fact of p smaller than alpha is not likely going to happen if null hypothesis was true. So the conclusion is that the null hypothesis was not true. Then we should reject it. That's the logic here. Okay, it's not that straightforward. It's like one circle inside another circle, but try to read the text, do some practice and repeat the slides and maybe this video to figure out, okay? So for the last part of this lecture, I'm going to compare hypothesis test and confidence intervals we learned last lecture. And I mentioned at the beginning of this lecture that alpha exists in hypothesis test, right? It also exists in confidence interval establishment. So what's the connection between these two inferential methods, okay? So confidence interval provides plausible values for mu, where plausibility is defined in terms of having a p-value larger than alpha. So basically, we use this formula to establish an interval of mu. Okay, and the probability of mu within of the actual mu within this interval is equal to 1 minus alpha. So this is the meaning of confidence interval, right? For example, alpha equals 0.1. Then what we're trying to do here is to find out an interval that the probability of true mean within this interval is 90%, right? Because alpha equals 0.1. Then the right side of this formula is 0.9, which is 90%. 90% is the confidence level here. Okay, now let's talk about hypothesis testing. A two-sided hypothesis test with alpha as significance level rejects the null hypothesis exactly when the value mu0 falls outside of this confidence interval. So mu should be within this interval, right, with a confidence level of 90%. But if your actual mu0, it is outside this 90% confidence level interval, then the null hypothesis should be rejected. So that's the connection between confidence interval and two-sided hypothesis test. So what does it mean? So here, I'm using this old graph showing you the do not reject range and reject range defined by two critical values, z half alpha and z and negative z half alpha. And if the null hypothesis is true, then your actual mu value, mu0, should within this range from negative z half alpha to positive z half alpha. So the center of this equation the ratio between this numerator and denominator, this specific value should be within this interval from negative z half alpha and positive z half alpha. Okay, that's how hypothesis testing is connected to the estimation. When alpha is decided, 1 minus alpha is decided. Then if the hypothesis, null hypothesis is true, your z value should be within the range or the interval established by these two critical values. If this specific value, the formula, the value for this specific formula is falling outside this range, which means the actual z value is within this shaded area or that shaded area, then we say we reject the null hypothesis. Okay, so estimation and hypothesis testing, they are connected by alpha. So let's just use the shopping trips example to connect them. Okay, so here let's just use employ and or carry out a two-sided test. The null hypothesis is still mu equals 3.0, so 3.0. And alternative hypothesis is that mu is not equal to 3.0, or 3.1, sorry. So to test the null hypothesis at significant level alpha equals 0.05, we can use a 95% confidence interval for mu. If alpha is equal to 0.05 and we're doing an estimation, then the confidence level should be 95%. And the confidence interval we're going to create is called 95% confidence interval, right? So this is how we create this CI, confidence interval, right? Mu should be larger than this value, smaller than this value, and these two values, they are about x bar, z half alpha, the standard deviation of the sample, and the sample size. Okay, so let's make it more specific. So eventually, you know that when alpha is equal to 0.05, the 95% confidence interval should be between 3.62 and 5.18. This is the interval you get from estimation. Okay. So 3.1. Mu equals 3.1. That's our null hypothesis. Is 3.1 inside this confidence interval? Of course not, because 3.1 is smaller than the left boundary of this interval, which is 3.62. So 3.1, which is mu 0, is not within the interval. Then we reject H0. So you can see here, we did not calculate the z-test. We did not even find the critical values for hypothesis testing. We created a confidence interval and used this confidence interval to decide if we should reject H0. What did we do? We compared the value of mu 0 and the confidence interval we just created. If that mu 0 is within this confidence interval, then we do not reject H0. But here, 3.1 is actually outside of this confidence interval based on this specific alpha value, so we reject H0. So you can say here, alpha is something connecting hypothesis tests and confidence intervals. Okay, so I mentioned at the start of the semester, of the lecture, and alpha in hypothesis testing and alpha in confidence interval estimation, they are actually the same thing. Okay, Okay, that's all I want to talk about one sample test or one sample hypothesis testing. Next lecture, we're going to compare two samples. Here, we compare sample mean with a specific value. Next, for two samples, we're going to compare their means. Okay, but before that, please try to use some time to make sure that you understand what I have talked about hypothesis test. And like I advised before, do some exercise. Make sure you know what you're doing. Okay, and those several steps for hypothesis testing, they are something you need to memorize. Okay, not memorize, at least you should know what you need to do first for hypothesis testing. What's the second step? What's the third? How to get the conclusion about reject or not reject the null hypothesis. Okay. Okay, thank you. I'll just stop here and I will see you in the next lecture.